Japanese garden bridges used to have a symbolic meaning along with a practical one. A bridge symbolizes traveling in transition from one state or world to another, like from the world of humans to the world of nature to paradise and immortality. Hi, my name is Dr. Hu, and let's create a bunch of those for ourselves by learning how to make a Japanese bridge generator from Megascans using Houdini and Unreal Engine. Before we begin, just a quick disclaimer that this is a short version of the tutorial, which should give you a very good idea of how to make your own bridge generator. But if you need project files or step-by-step tutorial, you can access them by supporting us following the links provided. Please keep in mind that by supporting us, you're not only supporting creation of more tutorials like this, but also our indie games. So, yoroshiku onegaishimasu. I usually start by gathering some references of what I'm gonna build. I'm not gonna stick to any specific, but just to get a general idea of how Japanese bridges are built. Then I would go to Quixel bridge and try to find the assets I would use to build this bridge. And this is a list of assets we're gonna use. So go ahead and export them into Houdini. Here we are in Houdini. This is a list of assets that came from the bridge. I just grouped them and gave them some labels for future reference. Let's go to the main network and take a look. So inside you see I've got a mannequin and my digital asset. I usually start with bringing a human reference into my scene for the scale. So I'll go quickly through the parameters of this generator. So we've got a bunch of input assets that are going to be passed from Unreal to Houdini. And the next one is a seed. It's basically a randomization seed. The length, you can define the length of the bridge, and targets width, it's going to be width, but actual width is calculated based on the length and actual tile size as well. So the reason for this, because we want to keep the tiles uniform, so we need to sacrifice width precision because of it. Next one is bend. It's basically self-explanatory. And basicness is for the layer under the tiles, just to fill in the gaps. Target tile size. Again, actual tile size is calculated based on the bridge length and how many tiles it actually can fit in, so it's going to be adjusted. And tile scale offset is just independent value to scale the tiles, maybe to add or remove the gaps between them. And broken tile weight is to add or remove more broken tiles. The next ones would be parameters for the railing and lanterns. So similar to the tiles, it's got scale and scale offset. And the last one is the lantern's density. Basically, if you play with it, you can define how many lanterns you're gonna see, and if you set it completely to 0, you will completely switch them off. And the last ones are for the beams. So if you take a look underneath, and I'm gonna play with this value so you can see the size of the long beams and the post change. And the last one is basically for the cross beam quantity. Yeah, so this is our generator. If I dive in, you can see I obviously start with a grid because of tiles. And the grid size is calculated based on parameters. Length is basically bridge length, and width gonna be calculated based on target width and tile size. So it's width divided by tile size and rounded it up to fit exact numbers of tiles. And rows and columns, and basically length and width divided by tile size. Next, I'm going to loop through every primitive and fuse them to a central point. That's where I'm going to instance my tiles. After that, I add a small weights function to add a 90 degrees random rotation to the tiles to give them a little bit of variation, and also create a variant attribute and randomize it as well. After that, just copy 2 points. Just make sure that variant attribute is switched on. I also created this small digital asset randomized transform that helps to add a little bit of imperfections in transformation to the instance geometry, which makes realistic objects more believable because it's all about imperfections, and noise is a big part of it as well. If I dive into one of these instance floor tile variants, you can see that I simply object merge the Megascans in here and created this function to make sure that it's not null and packed when it's coming from Unreal, and if there is nothing provided, I just have a little fallback in here. After that, I calculate the size of the tile based on our parameter and the length of the bridge, and add a little scale offset at the end. And this pretty much is done for every input asset from Unreal. This little transform is just small offset for this specific tile because it didn't match up with other tiles, just to align it a little bit better. And here we go. This is our floor tiles are pretty much done. Now we can move on to the base. The base is basically a floor surface underneath the tiles to fill in the gaps. First we thicken it, then we unwrap. Thickness is actually based on our parameter we created. Then we UV layout. So thicken, UV unwrap, UV layout. Then we harden sharp edges using soften normals node. Doing a little bit of cleanup by deleting unnecessary attributes. Give it a name. The first material is actually for previewing in Houdini. And the next one is the material is going to be used by Unreal Engine, and we have a parameter for that as well. Then we have a couple of bands, and the band and capture length attribute are based on our parameters too. Then we pack. Make sure you transfer Unreal generated mesh name attribute, that it's named correctly inside of Unreal. Now we can move on to the next one, which is railing. For the railing, I'm doing basically the same thing. I make sure it's not null and packed, and if there is nothing provided, I have a fallback. And then I calculate its size based on bridge length and railing target size. And I'm doing this for both of them. And after that, I add 90 degrees rotation. For this one, I need to select outside edges. So I create a group by object first. And I just scale the base and transform it a little bit and create this group of points. Then I promote them to edges and blast them away, so I end up with just these 2 curves. And this little branch is basically for the case when there is less than 2 columns, so I need to do it a little bit differently. I just group it based on bounding box, and I dissolve the edges, and this is basically the same result for different case. Then I add normals. If I switch them on, now you see the point in opposite directions. And polypass is just make sure that I have only 2 curves, 2 primitives, and then I resample them based on the bridge length and railing size as well, and I split them into sections. So if I enable primitive number, you can see that before it was just 2 primitives, and now it's like every section is separate. Next, I calculate railing offset along the normals based on its bounding box. I need to offset it half of its width to make sure it doesn't collide with the tiles. After that, I'll go through each of the sections. That's why actually I cut it into multiple sections. And I fuse them into the center points. That's why I'm going to instance the railing to. After that, I add the variant attribute and randomize it, and add random 180 degrees rotation. Then copy the points, make sure that this attribute is enabled, and in the end, I use my randomized transform digital asset to add a little bit of subtle variation. Lanterns is basically the same thing. We make sure it's not null and packed with fallback, and instead of the size, we just have a simple scale bound to our parameter. After that, I just use the same curves I used for the railing and offset them by lantern size, and I calculated the offset based on the bounding box, same way as before. After that, I go through each of the curves, sort the points. So for this one, I need to make sure that the lanterns go in between the railings. I just use the group range node with the density attribute to grab every endpoint on the curve. And I also make sure that I grab endpoints as well. After that, I add random rotation 90 degrees, same way as before. Copy 2 points, but this time without variant attribute because we got only single asset. And in the end, we add a little bit of transform randomization. And this switch node is actually that in case the density is 0, then we spawn nothing. And we can move on to the next one. Next, we can move on to the crossbeams. So we start with the grid. It's basically the same dimensions as the original grid, plus the bounding box of the railing, multiplied by 3. So the idea behind it is that we want it to stick out a little bit beyond the railings. Then we add normals to point outwards, and then we carve 2 lines out of the grid in the middle. That's where we're gonna instance our crossbeams. So we sample them based on the crossbeam count parameter we have, add a variant attribute, and then random rotation. And in the end, we just copy points. This transform, it just offsets it based on the crossbeam size plus by thickness. So if I go all the way here and take a look at the underneath, you will see that it just snaps the beams into the right spot, that it sits just exactly underneath. And on the right side is, I wanted to add a few more beams at the endpoints of the bridge. So I grab the same cross beam and I just justified differently. So if you take a look from this side, then you can see I just push it to the left. Then when we instance it at the endpoint, they all face the right direction. So we add normals pointing outwards at the endpoints and just copy to the group. And in the end, I just add a little bit of random transform and our cross beams are done. And now it's time for the long beams. I'm going to use the same curves, the ones I've used for the cross beams, and I'm going to resample them based on a long beam size. Then I'm going to slice them into sections and fuse them into points, add variant attribute, a random rotation, and a vertical offset in the end, basically pushing down based on the crossbeam height and the bridge itself, and then copy 2 points. Adding a random transform at the end. So now this bit is a little bit tricky because we need to bend this one, and we cannot bend pack geometry. We need to unpack it first, and then we would be able to bend it same way as before. We also need to add Unreal generated mesh name, because it's going to be Houdini generated geometry now, not instances, but because we preserve Unreal material, it's gonna assign both of the materials back to generated geometry. So this is actually pretty cool because when we use geometry as parameters, Unreal passes all the Unreal parameters into Houdini, and we can use it and propagate it back into Unreal when we modify the geometry. Now let's move on to the railing beams. What I mean by this, if we go all the way down here and look underneath the railing, and if I cut this wire, you can see there is a gap between the railing and the cross beams. So we want to close this gap. So first thing, I would grab the cross beam and I would rotate it 90 degrees, make sure it matches the scale of the railing. So if I point at this wire, you can see it goes all the way back to the railing. So I match its scale to say within bounding box of the railing, and then I do it again just on the x-axis to stretch it, and then I split both beams and justify them on y-axis separately, just to make sure they match up a little bit better. And then I copy 2 points. I use exactly the same points I used for the railings. If I zoom out, you can see this wire goes all the way back to the railings. And I use exactly the same random transformer what I used for the railings to make sure they match. And last but not least, so we are basically gonna grab the same points that I used for the long beams and add a random 90 degrees rotation and copy the posts 2 points. And if I dive inside, I just match size to the parameter we defined for the post size and add 180 degrees rotation just to set the proper orientation and randomize it randomly. If we go here, so we still need to bend all this packed geometry together separately from the ones we already generated and unpacked. So we're doing the same 1 and 2 bend, and this is the other 2 meshes that we actually bend separately, and we merge them together. And this last step is actually quite interesting. What it does, it replaces all the packed geometry with Unreal instances. It's basically points with all the attributes that required by Unreal. I'm not gonna dive inside of this because it's not a critical step, because it can be done manually inside of Unreal. But to give you an idea, what we basically do is to read intrinsic transform properties from packed geometry and then copy them into points and delete the actual packed geometry from there. So, and as a result, we can pull the instances automatically inside of Unreal Engine. So all we need to do is to set proper references to point to the right meshes inside of Unreal. So this is our digital asset inside of Unreal. So you can see it's got pretty much the same parameters. If I change lengths and it cooks for a bit, then we should see that it changes the lengths. It seems to be working, looks pretty cool. Maybe width as well. Yeah, let's set it back to default ones. So what we've done in Unreal, we've exported all the Megascans from the bridge into Unreal, all the same ones, and then I went to the default Megascans material and modified it a little bit. I've added some color variation based on world position of the instances, and also added some noise color variation, which basically applies to both color and roughness as well. I've also modified this lantern. I've created a new blueprint, and inside there is a lantern mesh and light source mesh. Light source mesh is basically like a squashed sphere that with a missing material that represents a light bulb, and we have the light itself. Then I have this flicker lights function that based on min and max light intensity and time scale. So first we grab actor location to get a random number based on position, and then we add time in seconds and generate a bunch of Perlin noise, multiply it together and set intensity of both light and light source mesh emissive material. Then if I go to event graph, I can plug this to eventic and also in construction script to make sure it works in the editor. Just you need to make sure that the function can be executed in the editor as well. So there is a checkbox that you can take. And this is it. You can duplicate the digital asset and generate as many bridges as you want. Congrats! If you like this tutorial, please subscribe and share with your Houdini and Unreal friends, and don't forget to support us.